Hart from University of Cambridge speaking, and he will talk to us about the random quantum from compact localized state to many body scars. So Oliver is doing his PhD at the University of Cambridge with Claudio who was talking here last week and who partially advertised this talk as well. Oliver is in general interested in interacting, frustrating many body systems and when they're actually quantum. So please, Oliver, the stage is all yours.
Thank you, Alexei, for the introduction and the invitation to speak here. As you said, I'm going to be talking about the random quantum cone, which is a model that we've introduced to sort of describe quasi-particle motion in quantum spin liquids. But I'll really get onto the motivation in a second. It's all about this work that we posted recently on the archive here. So just so that we're all on the same page, by random quantum cone, I mean a system that contains a one-dimensional backbone consisting of a one-dimensional string of sites and then offshoots that are placed off the backbone, which we're referring to as offshoots. So in principle, the offshoots can take any form. You can stick sort of an arbitrary Hamiltonian coming off each site. But for simplicity and for correspondence with spinice, we're considering the scenario when the offshoots are linear. So there's one offshoot per site, and its length is a random variable drawn from some distribution. So why would you ever want to study a random quantum cone? I'm going to try and convince you that these random cone-like structures are relevant to the motion of quasiparticles in spinice. So kind of carrying on from Claudio's talk last week, we're thinking about sort of frustrated magnetism, models of frustrated magnetism, and how their quasiparticle excitations behave. And I'll show that essentially what happens is the motion of the quasiparticle, rather than hopping on the lattice in real space, is kind of confined to some tree-like structure in configuration space. And then understanding the motion of the quasiparticles reduces to understanding the motion of a type binding model on sort of a random tree-like structure. In general, cone models are actually, they've been used before, but sort of more in a classical context, really, as an example of sort of structural randomness. So, for example, in classical percolation clusters, where you start removing bonds at random from some lattice, there you can kind of think about quasi-one-dimensional segments of the classical cluster and think about motion of particles on that random structure. In the classical case, if you have these sort of linear offshoots, you can imagine a particle sort of hopping along the backbone, and occasionally it can hop off onto one of the offshoots, and then it'll spend some characteristic time on that offshoot that depends upon its length. And if that length is a random variable, you essentially have some characteristic trapping time on each site that is distributed randomly, and therefore you can obtain sort of interesting motion in classically, such as like subdiffusion and other things. So it's sort of basically a simple model of structural randomness that allows sort of simple analytical modeling and numerical methods, which is simpler than sort of studying directly the percolation cluster itself. And in the quantum case, even in the case of infinite translationally invariant offshoots, so when every site has an infinite one-dimensional chain sticking out, even that case exhibits interesting dynamics. So it's shown that if you take that system and you project the motion onto the backbone of the system, then the equation of motion for the wave function on the backbone is then non-unitary, because some of the probability can be lost to the offshoots. As you have a particle hopping along the backbone, some of the probability can be lost, and that non-unitary evolution can correspond to some fractional time Schrödinger equation where the normal time derivative is replaced by some fractional time derivative. So that's why we want to study the cone. But now I'll try and make this correspondence with models of frustrated magnetism more concrete. So this is kind of following directly on from Claudio's seminar last week. So he introduced this 6 vertex model, whereby you have the sum of the 4 spins around any vertex on the square lattice. So you have these Ising degrees of freedom that live on the bonds of a square lattice that point up or down, plus or minus 1. In order for this sum of spins around the vertex to be vanishing, there are sort of 6 possible vertices that are compatible with that constraint. You can either have the 2 like charges next to one another, of which there are 4, or opposite one another, and then there are 2. So there are 6 vertices compatible with that constraint, and hence the name. So this constraint is imposed in a hard way with this delta function, but you can also think about introducing it in a soft manner by taking the argument of the delta function and squaring it. And that means that any non-zero sum is given some finite energy cost. So if it's enforced in a soft way, excitations are allowed in the model, but they have some finite energy cost that appears in front of this sum. And then to reintroduce the hard constraint in a classical model, you just take temperature to 0, or equivalently at finite temperature, take the energy scale to infinity, and then you reinforce the hard constraint. So imposing this Hamiltonian on the easing degrees of freedom on this square lattice, we then end up with sort of that's what's known then as sort of classical square ice. So we can then write down sort of ground states of the model, and they correspond to these 6 vertices. And in this arrow language, a sort of an arrow goes from the A to the B sublattice if it's a plus, and from the B to the A if it's a minus. And then every single vertex will have 2 spins pointing in and 2 spins pointing out, and this is a ground state. Excitations then correspond to flipping spins. And if you flip a single spin, you'll create 2 defective vertices next to one another. And those 2 defective vertices can then be moved apart by flipping spins in between. So that's like a very brief review of Claudio's seminar last week. And now I'll sort of take it from the 6 vertex model to spinice, although I will end up going back to square ice again in the end. But in order to introduce the concept of the microscopic tree, I think I need to introduce this lattice, unfortunately. So now moving from square ice to spinice, the spins now, rather than living around vertex on the square lattice, we now have the spins living on the sites of a pyrochlore lattice, which is a lattice of corner-sharing tetrahedra. And now we can, so schematically, we can think about replacing the physics of a vertex with the physics of a tetrahedron. So rather than having the sum of the spins around a vertex, it will now be some of the spins belonging to a given tetrahedron. The charges or excitations will then live in the center of these tetrahedra, and the centers form a diamond lattice in 3 dimensions. So the ground states, as before, corresponds to charge neutral tetrahedra with 2 spins pointing in and 2 spins pointing out. Excitations correspond to violations of the local constraint, and they would correspond to 3 spins pointing out. Sorry, 3 out, 1 in, or 3 spins pointing in and 1 out, and those correspond to charges +1 and -1, respectively, and they cost an energy which is of order J effective in this notation. So just to reiterate, if you have a section of the pyrochlore lattice now which is satisfying the ice rules, so every single tetrahedron is charge neutral with 2 spins in, 2 spins out, you can then flip, for example, this spin, produce a positive and negative pair of monopoles, so that this one is now 3 out, 1 in, this one's 3 in, 1 out, and we can then move the monopoles apart by flipping further spins. And the 2 charges are then separated by this string of spins, which points from the positive to the negative charge. So again, it's sort of the same as in the 6 vertex language. So now on to the sort of important points that lead to a difference between the quasiparticle description. Lead to the difference between it being just a normal free particle and it really being sort of an emergent quasiparticle that's defined by the underlying spin configuration. So if it really were a particle, then it would just be, some classical object that lives on the diamond lattice. And then if it exists on a given site, it would be able to hop to any of the 4 neighbors around that site. But that's not the case because the charges are, in fact, defined by the underlying spin configuration. and so their motion is not entirely unconstrained from the spin background. In fact, the motion of the particle is strongly correlated with the spin configuration of the lattice. So if you have a positive charge, it's defined by one spin pointing in and 3 out. And so there are 3 majority spins and 1 minority spin. If you try and move the monopole along the minority direction, if you flip this spin in red, you'll then change this tetrahedron to being all spins pointing out, which, rather than being a monopole move event, is a creation of a double charge on this site, because it's all spins pointing out, which corresponds to a charge of +2. So that means that there are actually only 3 directions that you can move the monopole in, and systematically 1 out of 4 of those directions is blocked. So just as an aside, this can give rise to some very interesting behaviour in classical spinice when the system is driven out of equilibrium. So if you have a positive and a negative charge that are separated by a minority spin, so a block direction, that pair of charges is then known as non-contractible, because flipping the spin in between, if it were a majority spin, you would just annihilate the pair and get back to the vacuum on both sites. But if it's a minority spin, you actually can't annihilate the pair, and you just create an adjacent pair of double charges instead. So they correspond essentially to a metastable state, because in order to annihilate the pair and get to lower energies, you have to separate the pair and annihilate them somewhere else, which costs energy. So if you quench low temperatures in spinice, then you end up with this metastable plateau in monopole density as a result of these non-contractible pairs. But that's really sort of an aside, and it's just sort of showing you one feature that arises as a result of this minority spin. So one other feature that was sort of recently noted in this PRL by Bruno Tomasello is that, again, there's another constraint on monopole motion, but this time it's relating to kind of how monopoles hop in the first place. So if we think about semi-classically what needs to happen for this monopole to move from the bottom left to the top right tetrahedron, this intervening spin needs to flip. And in order for a spin to sort of rotate and flip, it needs a transverse field component in order for it to sort of process around that magnetic field and rotate into the other tetrahedron. So, what is providing that magnetic field? Well, it's the neighboring spins. So if you just look at the local field, which is just the sum of the spins that are neighboring to this central one, so these 6, if you sum up their local magnetic moments and then look at the local field acting on the central spin, if it has a transverse component, the spin can then process around that field and move the monopole. But it turns out that in 1/3, stochastically, of the remaining of the configurations, there's actually an exact cancellation between spins, and there's no transverse field component, which means that this spin is frozen. If you include the contribution of spins that are further away than just nearest neighbor, then rather than being exactly frozen, it just has a slow timescale for hopping, which is sort of orders of magnitude slower than the fast timescale. So sort of quantum mechanically, we have these sort of two states, and they either have basically a finite matrix element for the transition or 0 matrix element. So this is another constraint on the motion of monopoles. This time it's stochastic as opposed to deterministic, but nevertheless it constrains rather the motion of the charges moving throughout the lattice, and it correlates the motion with the background spin degrees of freedom. So they're kind of inextricably linked together. So we're now sort of in a position to actually construct one of these microscopic trees. So at the beginning of the talk, you might have thought that if we called this thing a quasiparticle, it could probably move sort of up, down, left, right, and just freely propagate throughout the lattice. But we now know that's not true. So by the way, these green spins are meant to represent sort of locally creating a pair and then moving the neighbor off to infinity, so that you then have some sort of isolated charge in the center of the lattice. So I know it's a bit small, I'm sorry, but you can probably see that the up spin is the spin sort of in the up direction is the minority one. And so only sort of left, down, and right are sort of in principle allowed by virtue of not being blocked. So left, down, and right are the majority spin directions. So we would think that in principle, okay, it cannot move up, but it can go left, down, or right. But again, that's not quite the case, because it turns out that if you look at this spin configuration, it's easier to look at this called zoomed in version. The yellow spins rather cancel with one another, so do the reds and so do the blues, which means that this spin in the middle here is frozen, and so the monopole can't hop left. If you then sort of repeat this procedure, you can look at all sort of adjacent spin configurations that move the monopole, that are consistent with energy conservation, and they don't go along a block direction and they don't go along a frozen direction, and that leads to this sort of microscopic tree on the right. So if the monopole goes down, it turns out that all of the directions then are then sort of not allowed, and so the tree is truncated. And if you sort of continue this procedure, you'll end up with this sort of microscopic tree-like structure in configuration space. So by configuration space, that just means sort of the space of the spin degrees of freedom, rather than sort of the position space of the monopole position, because there are sort of multiple spin configurations for each real space position of the charge. So this network is sort of locally tree-like, but it does in principle include loops on larger length scales, but those are sort of not relevant for the discussion of this right now. So as a brief aside, it turns out that microscopic trees and sort of fractal lattices in general are actually sort of a very useful way of describing quasi-particle motion in spin liquids in a particular temperature regime. So again, I think that this temperature regime is something that Claudio mentioned last week, but I'll just sort of sort of reiterate that. So you have two different models here, the 8 vertex model. So the product of all spins around a vertex must be +1 in this classical model. And on the right, we just have classical spinice on the pyrochlore lattice. So you have a macroscopically degenerate ground state manifold and a degenerate first excited manifold as well in the classical model. We can then turn on the quantum piece. So in the 8 vertex model, some transverse field, and in classical spinice, making it quantum spinice, this perpendicular sort of hopping term for the spins. So in the ground state manifold, you end up with perturbative processes called ring exchange processes that broaden this ground state sector to something that's order h to the 4 for the 8 vertex model and order j perpendicular cubes for the XXZ model. Excitations between the sectors, the sectors are still separated by either j or jz, but in the first excited sector, the perturbation acts within first order perturbation theory and gives you either h or j perpendicular respectively for the two models. But if you then put temperature sort of in between these two energy scales, you then have an incoherent mixture of the ground state manifold. And if you then have a particle moving through that incoherent mixture of ground states, that's essentially, and very hand-wavingly, what gives you the restriction to some microscopic fractal lattice. So for example, in the 8 vertex model, excitations within the ground state manifold correspond to the excitation of these pi fluxes, whereas states in the first excited sector correspond to the tight binding motion of some particle on the square lattice. And then if you take an incoherent mixture of all possible pi flux states, you then essentially restrict the particle to move along paths that don't enclose any area. Because if you enclose a pi flux, the path will end up giving you a zero contribution. So essentially, the motion of the particle is restricted to some beta lattice in the 8 vertex model, And via a similar argument in quantum spinice, you end up with a restriction to this Cassini cactus lattice. But in both cases, the microscopic tree gives you a much more accurate description of the physics than just taking the original particle, hopping on the original lattice. And that's basically saying that the particle is strongly coupled to the underlying spin degrees of freedom. So back to the problem at hand, we have this random tree-like structure where the average number of dynamical spins around any given monopole is 2. As I mentioned before, the structure is sort of locally tree-like, but does include loops on larger length scales, which are not going to be spoken more about here. And then basically, once we have this cluster of classically allowed transitions, we can then sort of generate quantum dynamics by adding back in the matrix elements for those transitions. And this gives you sort of an effective type binding model in configuration space. So that was the process that was studied in this work by Matthew Sterling collaborators, where they're actually sort of defining these structures from the original spin configurations. And in this work, we're kind of taking a more abstracted approach, thinking about quasi-one-dimensional segments of this random structure and sort of modeling them and seeing what behavior we can get out using this random comb model instead. So again, to remind you, we have a one-dimensional backbone with hopping parameter T1, and in principle, the hopping parameter in the offshoots can be different. So if we're just thinking about it as a percolation cluster, there's no difference between a bond in the offshoots and a bond on the backbone. But if we're thinking instead about a model of some main chain plus sort of dendritic random offshoots, then in principle we should allow for the hopping parameter in the offshoots to be different, and then the length of these one-dimensional offshoots is drawn from some random probability distribution. So here we're taking a power law, but it turns out that actually, the physics is not particularly dependent upon the particular probability distribution that you choose. We were thinking initially that potentially the heavy tails of the power law would have some interesting effect, but it really turns out that as long as the mean length remains finite, the physics remains almost unchanged. So now to study the single particle physics on the cone, perhaps unsurprisingly, because we have a one-dimensional model with sort of local disorder and statistically independent disorder on each site, the model is entirely localized. So the entire spectrum for any energy and for any ratio of T2 over T1, apart from trivially T2 equals 0, where there is no disorder, the system is entirely localized. So just quickly, for those of you that aren't familiar with the transfer matrix method, people that have seen it before, won't be needing to do this, but just in case no one's seen it, if you have a wave function on site X, you can relate it to the wave function on the site before it via this transfer matrix T of X, which depends on energy. But you can then iterate this condition, this relation, sort of down the chain to relate it to the site before that, and continue going until you reach the end of the chain. So then you're left with this product of transfer matrices, which in general grows exponentially with the length of this sequence, and the characteristic length over which it grows asymptotically is the localization length. So the rate lambda is known as the Lyapunov exponent, and the reciprocal of that number is the localization length. So the way that this product asymptotically grows is related to how the wave function asymptotically decays in real space. So then there are two sort of key features to take away from this plot. One of them is that you have these lines of zeros in the upper triangle, and the other feature is this sort of fin of not delocalized states, but very weakly localized states with a very long localization length at the bottom. So we need to understand those two key features, the lines of zeros and the states with a large localization length. So these these lines occur at very particular values of the energy, or ratios of the energy to the bandwidth of the offshoots. And so that kind of gives us some insight as to what might be causing them. So to explain where they come from, we can imagine taking a particular region of the lattice, and then with some finite probability, you'll generate these clusters of sites that are symmetric with a finite density. So for example, here, a sort of a 2-1-2 configuration of offshoots. So then if we imagine cutting the bonds on either side of this cluster and removing the stuff to the left and removing the stuff to the right, we can then think about locally diagonalizing this 8-site cluster and seeing what we get. So I mean, normally that wouldn't be a particularly useful thing to do, because you would obtain 8 eigenenergies and 8 eigenstates. But then when you glued it back into the rest of the chain, everything would mix together and you wouldn't really have learned anything. But it turns out that in this case, the cluster has a very special structure such that the wave function has exactly 0 projection onto sites 3 and 5 in this notation. So you can see there are exact zeros here in the wave function. And that means that when you glue this eigenstate back onto the rest of the chain, it remains an exact eigenstate of the full system. So basically, by just sort of identifying this local cluster and diagonalizing it locally, you can find exact eigenstates of the full chain, the full comb, but with strictly 0 localization length. So for this 8-site cluster, the energies are at plus minus T2, so the hopping parameter in the offshoots, and this particular cluster is responsible for the line that had the ratio of a half. But of course, there are other lines, and so perhaps it's not surprising that this argument can be generalized to get an entire family of compact localized states. So instead of having the 2-1-2 case, we now have generic lengths on sites x minus 1, x, and x plus 1. And if we have the same sort of symmetry requirement that the 2 lengths on either end, this one and this one, are the same, then there's a restriction that's placed on the intervening length on the central site. So if these 2 lengths are the same, then you'll obtain a compact localized state of energy En, where these energies are given by the eigenenergies of a one-dimensional type binding chain with open boundary conditions, if the ratios of the lengths multiplied by n satisfy the constraint that they must be a natural number. So you take this ratio multiplied by n, and if that's a natural number, then you will get a compact localized state. That's just sort of how it works. But this construction allows you to generate basically a compact localized state for any energy. So sort of re-understanding the 2-1-2 case, the lengths on either end are 2. So we can then kind of look at the formula and see what intervening lengths are allowed. And it turns out that if the middle length satisfies the condition 3 times an integer minus 2, then it will host a compact localized state at energy T2. And obviously 1 is a member of that set, and so as expected, it does host a compact localized state. But we've also then identified like an entire family of states that have energy T2. So if this intervening site has an offshoot that is of length 1, 4, 7, 10, so on, you'll get a similar compact localized state. So using this construction, you can obtain compact localized states for any energy En that has this form. And yes, that's how it works. So now you can consider, just as an aside, really, compact localized states in other systems. So even though we've identified them in this random structure, they're present more generally even in translation invariant systems. So if you just take this 212 formula unit and then tile that throughout space periodically, so just having a one-dimensional chain with this unit cell, there's then an extensive number of compact localized states with the same energies, and so you obtain two flat bands at energies plus minus T2, while the rest of the bands are dispersive. If the compact localized states span more than one unit cell, they're then not orthogonal, but you can construct exponentially localized orthogonal Wannier-like states if you take the appropriate superpositions of the compact localized states. All of these ideas can basically be generalized if you don't have a one-dimensional backbone, but you instead have sort of a 2D backbone. I suppose backbone isn't really then the right phrase for it, but sort of a 2D lattice augmented by linear offshoots. You can still get similar compact localized states in that scenario. But all of these one-dimensional examples can be understood in this nice work of Alexei and Sergey about classifying these compact localized states using this sort of universal flat band generator in D equals 1. So these ones that we found are all basically special cases of their sort of general framework. So now we're back to sort of comparing the random cone model with quantum spinice or quantum square ice. So the relevant one to be looking at here is the blue constrained model. So the other ones in here correspond to slightly different variants of the tree structure, but the constrained one includes both block directions and correlated monopole hopping. So both blocked and frozen directions essentially. And so in both cases, we have these delta-like peaks that on the left are arising because of compact localized states. So there's an extensive number of states with the same energy at 0, -1, and also at these lower energies as well, although the number of those compact localized states is significantly reduced with respect to these larger peaks. And basically we see the same behavior in quantum spinice. So we have these delta peaks at similar energies, +/-1, 0, and so on. But it turns out actually that in quantum spinice, the reason for this is twofold. Not only do you have compact localized states, but also because you're working on a structure that's generated randomly, you can have clusters that are of finite size with finite probability. And clusters with finite size will have a discrete spectrum, and therefore you'll also get discrete peaks as a result of that effect. But we've identified that not only do you get peaks due to discrete energy levels, you also have these compact localized states that live within certain regions of the percolation cluster in those microscopic trees. So everything can kind of be understood within this sort of unifying framework of integrating out the offshoots. So if you have the cone model and you think about integrating out the offshoots to give you some self-energy, the self-energy will depend on the length of the offshoot locally, but also on the energy of the particle propagating throughout the network. And so what you end up with is sort of an effective one-dimensional Anderson model, but with a disorder potential that depends both on energy and on the length, which means that your disordered potential takes this funny form. So L is sort of the random variable, and K parameterizes the energy through this expression. And then basically, if K over pi is a rational number, then you'll get a compact localized state, and the localization length is strictly 0. Whereas if K over pi is not rational, so it's irrational, the state is conventionally localized in the sense that the wave function decays exponentially at large distances. But now this framework also allows you to understand the region of states with a very long localization length. Basically, this disordered potential outside of the bandwidth of the offshoots becomes not a ratio of signs, but a ratio of hyperbolic signs, which then decays exponentially with K or equivalently as sort of a power law in E. And that gives you very weak disorder and therefore very large localization lengths within this region. So this framework of integrating out the offshoots gives you this nice sort of unified description of all of the possible cases. So now we can kind of take a step back and think a little bit about the cone model in its own right. So we're kind of diverging a bit from the original spinice motivation, but nevertheless kind of treating the cone model as an interesting thing to study in its own right and thinking about adding interactions on the cone. So for simplicity, we're now going to focus really on the translationally invariant model, although the results do really kind of apply to the random structure as well, but it's just easier to demonstrate the results numerically on a translationally invariant structure. So now what we're thinking about doing is adding an interaction energy scale U between adjacent sites on the cone. And there are kind of two options really. Either you take the viewpoint that it's kind of a bit like a percolation cluster, and therefore there's no difference between sites belonging to the backbone and sites belonging to the offshoots, in which case you would use the same value for U everywhere. Or you can take the perspective that you know, the sites on the offshoots are somehow distinct from the sites on the backbone, and in that case you would use a different value for U for the backbone and on the offshoots. And we're kind of going to take this latter approach and think about having a finite interaction on the backbone and keeping the offshoots non-interacting. I'll try and say something about the general case of having the same interaction scale everywhere, but for the moment, let's just focus on having interactions along the backbone only. So if we have this interacting system, we can compute the level statistics, for example, and we obtain a system that within each sector has nice sort of Ignatyson statistics, which suggests that the system should, is basically saying that the system is quantum chaotic and will thermalize on order 1 timescales. So basically, if we start with a generic infinite temperature eigenstate of the system, we would then expect observables to thermalize, so you know, equilibrate to their thermal values within timescales that are order 1 with respect to the energy scales in the Hamiltonian. So we can kind of check that prediction by looking at this sort of product initial state, putting 1 particle per unit cell, and then computing something like the return probability. And we see that rather than getting thermalization, you obtain long-lived oscillations in the return probability, which are kind of oscillating around a value, or the characteristic magnitude of those oscillations is significantly larger than what you would expect from a thermal state. So basically, the many-body state is kind of living within some much smaller manifold of states and not decaying to the thermal value that you would expect having looked at the level statistics. So why is that? Well, if we take the initial state and project it onto all of the eigenstates of the model, or all of the eigenenergies, we obtain a plot that looks like this. Whereas if you do the same thing for a random state, a random initial product state in real space, you obtain instead a distribution of overlaps that looks more like this. So evidently the difference between the two is this band of special states with a very large projection, the initial states with a very large overlap onto these atypical states, which are equally spaced in energy. And this sort of equal energy spacing is what's giving you sort of a characteristic timescale for the oscillations in the return probability. So what is the reason for this? So it turns out that for all values of parameters, so for all T1, T2, and U, the compact localized states that we've described before are in fact not only eigenstates of the non-interacting model, but they're also exact many-body eigenstates of the interacting model if you take a Slater determinant of compact localized states. And the reason for that is that the interaction operator, if you act on a slated determinant of compact localized states, then the interactions annihilate the state. So basically the compact localized states belong to the null space of the interaction energy operator. And this means that basically the slated determinants of compact localized states are sort of special area law states in an otherwise thermal or volume law spectrum, which means that they kind of constitute examples of many body scars. So they're sort of an exact example of many body scarring. And this is sort of a bit reminiscent of the classic sort of Shirashi-Mori construction for scars. So in this case, it's another way of obtaining a small number of states that are area law in an otherwise volume law or thermalizing spectrum, which give rise to sort of weak ergodicity breaking in the same manner that we've seen here, that if you start with a special initial product state, or sorry, just any special initial state that has a finite projection onto the scar states, then you'll obtain sort of non-thermal behavior, even though a generic initial state will probably still thermalize. But in their construction, you have these local projectors Pi and local operators Hi, and some other piece of the Hamiltonian H primed. And if all of the local projectors commute with H primes, then any state capital psi that belongs to the common null space of all of the projectors Pi, then that state will form a many-body scar. So sort of the analogy is that, again, sort of states that are annihilated by a particular component of the Hamiltonian are what's responsible for the scarring. So this is for the case of interactions on the backbone only. If you use not the backbone only, but the same energy scale U everywhere, then you'll start mixing together some of the compact localized states, but the ones at zero energy will remain. So even in the case of having the same interaction scale everywhere on the lattice, so not just on the backbone, there you can still construct exact scar states, but just not at arbitrary energies. They must exist at E equals 0. Okay, so just to mention as well, compact localized states have been shown to survive the presence of interactions in other systems. So these other two nice papers by Sergey and Alexei, where they sort of showed that you can obtain sort of exciting things like many-body flatland localization in these systems. So there are other scenarios in which compact localized states can survive the presence of interactions. Okay, so I think that's me done really. So the conclusion is that we've kind of shown that these comb-like lattices are able to sort of, they have a really rich sort of nice localization structure. So they have both these compact localized states and conventionally localized states with exponentially localized wave functions densely populating the spectrum in energy. So at all rational wave vectors, you have these compact localized states, and at all irrational wave vectors, conventionally localized states. Everything can kind of be understood neatly within this framework of integrating out the offshoots to give you this effective Anderson model on the backbone, which gives you these two different regions of disorder. So sort of strong disorder within the bandwidth of the offshoots and a weak disorder outside of the bandwidth where it's exponentially suppressed. When you add interactions back onto the comb, you end up with the compact localized states still being exact eigenstates of the interacting model, perhaps surprisingly, which means that they actually form an example of exact many-body scarring. So they provide an example of sort of weak ergodicity breaking, so that if you choose a special initial state, you won't get thermalization, even though a generic initial state will thermalize. And all of this has got implications for sort of quantum spinice and other related models of frustrated magnetism, by thinking about having a quasiparticle which is moving on some random fractal in configuration space, And yeah, all of these features that I've described will have implications there. All right, thank you very much for listening. I'll be happy to take any questions.
Great. Thank you, Oliver, for this talk. Let us all thank our speaker. And, questions from the audience? Yes, Sergey, please go ahead.
Yeah, thanks, Ollie, for this very nice talk. Can we please go back to this simulation of the survival probability of the many-body state?
Yes.
Right. So can you again remind? So first of all, in that system, in that simulation, you have a disordered comp. Is that correct?
This one is translationally invariant.
Translation invariant.
Yeah, sorry, it's this one in the top right-hand corner using the sort of 2-1-2 configuration. Right. Although, so in principle, you would expect similar physics to happen in the random structure as well. It's just that you wouldn't, in order to see the oscillations, you wouldn't use a translationally invariant initial state. You would have to use a product state that kind of respected the structure of the random cone.
Mm-hmm. Okay, and then in that particular case of a translation invariant comp, then what are, so in the, let me put it that way, in the disordered case, you had states which were compact localized and exponentially localized.
Yes.
And what are the states, what happens here? Of course, I'm talking about the single particle problem.
Okay.
So there are, of course, compact states, but there's probably other states as well, or not?
Yeah, that's right. So if I go back to, sorry for moving around. This is the band structure for that particular case. So like you're saying, you've got both. You know, your unit cell has got eight sides, and so there are two flat bands at plus minus T2, and the rest of the bands are dispersive.
Good. And now you take an initial state, which is something. I don't recall what it was exactly for this survival.
Yeah, so it's one kind of. It has. Yeah. So this plot in the top right is trying to show like the structure of the compact localized state. So they've got sort of a finite projection onto the sites that are colored in blue.
Yeah.
And so the initial state that we're choosing has got sort of a significant, the initial state has got a significant projection onto these compact localized states because you know it's going onto this site with a blue dot. If you instead chose one where it was on these sites, for example, then you probably wouldn't get the same physics.
Okay. So and then you evolve that state in time, and you see this these oscillations which tell you that you have a few states you very strongly, so to say, in some sense overlap. Like, can you show again, please, this?
Yeah, so I mean, it'd be nice if I could have them both on the same page, really, but there's that band of states with a really large overlap. And so, for sufficiently short time, the dynamics is kind of constrained to that small manifold.
And the period, the typical period you see here in time is again related to which energy which you showed?
So it's related to the separation of energies here. So because basically the structure of the states here is that you've got a given number of particles, and so it just the particle number that we chose is half the number of compact localized states that there are on the chain, which means that you've kind of got the maximum number of freedom, the maximum freedom of putting different particles in different compact localized states. So then these different, because you've got two different compact localized states at plus and minus T2, depending on the combination of putting like all the particles in minus T2, all the particles in plus T2, or things in between, this characteristic separation is corresponding to like moving one particle from a minus T2 compact localized state to a plus T2 compact localized state.
Mm-hmm. But these energy differences or distances, they are slightly different, right? For different pairs of these atypical states. So you have 5 typical states, and then I can take difference between 2 and 1, 3 and 2, and so on. They are slightly different. Is that correct, or are they exactly the same?
I think it's exactly the same. I think it's sort of a visual artifact because this is a, it's a large distance, but the horizontal separation is the same for all of them, I think. So they should be happening at 0, 2, and, well, no, that's not right, is it? 0, 4, and 8, I think. But no, they should be exactly the same. Yeah.
Okay. Okay. Thank you.
Okay. More questions, comments from the audience? Well, it doesn't seem like. Maybe Alexei has something. Yeah.
Yeah, because I cannot find the button raise your hand.
Yes.
Now, actually, I have a few questions. So perhaps the first one is because depending on the statistics of the offshoots, you can generate different disorder. Did you consider generating, taking such a distribution of the length of the offshoots that you eventually delocalize the 1D model, that you get the effective 1D model?
So this, yeah, that's an interesting point, and it's something that we initially were actually more focused on. So the project kind of took a different direction. Initially, we're thinking more about the dynamics of the single particle model, how that depended upon the distribution of the offshoots. So sorry for skipping around. If I just go back to the this one. So we were taking a power law distribution of the offshoots, and then we were varying this gamma to sort of above and below the mean value of the length sort of diverging. So you could see how the behavior, how the dynamics changed as you moved from sort of below to above the mean diverging. That gamma equals 1. Sorry, gamma equals 2 rather. And yeah, that's something we were focused on, and it seems like there is a distinct difference in behavior. So if you look at the dynamics, you end up with some, I won't say. So you end up with sort of a transient power law dynamics where the power law of the spreading. So if you start, for example, with a single particle situated somewhere on the cone, and you then evolve time, the spreading of the particle transiently is subdiffusive, and the exponent was kind of, phase transition isn't the right word, but it sort of exhibited very different behavior below and above, the mean being finite versus not finite. So you do still get localization in the sense that even in the case where the mean is infinite, you still have something which is structurally random when you integrate out the offshoots, but you can still end up with sort of very qualitatively different behavior below and above, the mean being finite versus infinite. And I think, to be honest, it's something that we should have explored more more extensively, because the distribution of the disorder in the case where the mean is not well defined is also likely to be something that gives you very sort of interesting localization properties, where in the states where you don't have compact localized states, because that disorder distribution is kind of very singular and would probably give you very interesting localization characteristics.
Yeah, right. Well, yeah.
Sorry, maybe just intrude and ask a follow-up. So again, so if the mean is, so when do you see intermediate subdiffusion, as you call it, when do you expect it, for finite or for infinite, or averages?
It's for both, actually. So it's for both, right, but with different exponents. So there's some kind of discontinuous behavior in the exponent at the transition point.
What are the numbers?
Oh, well, I can't remember precisely, but in the classical case, you end up with something very similar, because if you have if you're in the classical case and you have infinite offshoots, you then have subdiffusion with exponent 1/2, and it then just becomes sort of faster and faster. So I think it then interpolates between sort of 1/2 and 1 when the mean becomes finite.
And you say it's intermediate, meaning that it's not asymptotic in time.
Yeah, because everything still remains, or at least within the timescales that we were able to access numerically, everything remains localized, because fundamentally the lattice is still disordered, and so there is still ostensibly some characteristic localization length at each energy. Or in any case, I mean, it might be the case that what do I want to say? It was only a transient behavior, and that it eventually did saturate to some value, although by varying the parameters T2 and also the distribution, you can obviously change that localization length and therefore the cutoff.
Okay, thank you. Sorry, Alexei, for interrupting.
No worries. No, I mean, when I was asking whether you could delocalize, I was thinking that one obvious candidate is where you take, I'm pretty sure that if you take the lengths of the offshoots to change quasi-periodically,
oh yes,
you will see delocalization. But I was thinking whether you can play a similar game with completely random. Well, not completely, but with some random distribution.
Yeah, no, that's an interesting point. Again, that's something that we actually wanted to look at, was a quasi-periodic distribution of offshoots, and then potentially, you do end up with some sort of transition in the localization properties from localized to delocalized, depending on the either the distribution or the parameter T2, depending. And yet we were also yeah, it was at one point we were also thinking about sort of the possibility of a many-body, localization, delocalization, transition, in the interacting model as well. But the system sizes that you can access there is, because you're adding these offshoots.
But well, technically you can always integrate them out, and then, or you're talking about the full model where you have interaction everywhere.
Yeah. So in the full model, exactly. Yeah. So in the interacting case, it's not possible to integrate them out in the same way, unlike in the single particle case where everything can be reduced to the backbone by getting rid of the offshoots by just integrating them out.
Okay, yeah. So then, actually, could you go to the page where you introduced the CLS? I have a very simple question.
So this one potentially, or the more general?
Yeah, that one is fine. I mean, is there actually a simple physical reason why the offshoots have to be equal in that case? I mean, if you want to get a CLS, why do you need the equal offshoots in this case, on this figure, in the up direction?
Okay, yeah. So the physical reason here is that in order to get zero projection onto this site here, it's the point is that, how do you want to phrase it? The compact localized state has an energy which is equal to one of the energies of this offshoot if it were isolated from the backbone. So that means that sort of the compact localized state takes the form of this length 2 offshoot, being in an eigenstate. And if you then look at the Schrödinger equation, if this offshoot is in an eigenstate, that means that the coefficients here satisfy locally the Schrödinger equation, and so you can't mix in anything from this site here. Otherwise, you'll then break it, which means that if both of these have the same length, they both have the same energy, and therefore both of these sites need to be 0 in order for these offshoots to have the same energy locally.
Okay, yeah, I think I get it. So I was thinking how you could break that, but the only thing that comes to my mind is when the offshoots stop being a chain and rather turn into something more complicated, then you can avoid that.
Yeah, so in the case, we actually, we considered the case of having, not just a linear chain, but having completely generic Hamiltonians connected to the site at each of them. And it turns out that this particular type of compact localized state is only present for the linear chains. If you try and play the same game with generic Hamiltonians like H1, H2, H3, if you set H1 equals H3, in general, it's not possible to kind of have that resonance condition for H2 if it's not a linear chain. So it's kind of not really a fruitful. It's not a nice type of compact localized state if you have complete generic Hamiltonians. Although you probably can construct, it would be possible to construct particular Hamiltonians that do satisfy the resonant condition, but then they're sort of very, very fine-tuned. Whereas the nice thing about this compact localized state is it's kind of the structure that's fine-tuned, but the compact localized state exists irrespective of the parameters.
Yeah, right. Well, I'm not sure that's directly related, but you might want to have a look at, there's a paper which constructs flat bands, and so the compact localized states in a bit similar way by that's a paper by Rodrigo Vicenzo, and it's titled, well, basically constructing flat bands and the compact localized states by making a repetition of clusters and joining them in a way that guarantees the destructive interference that gives you the CLS. So I think, well, I still think it's possible to fine tune the Hamiltonians, and I mean, but you're right. I mean, I cannot tell whether that would be generic in any way or not. By the way, Juzar.
Yes.
I mean, are there any other questions? Because I have more to ask. So I don't want. I don't.
Yeah, there doesn't seem to be any other raised hands from the audience members. So, but also if you have something very technical and specific, maybe it could be shifted after a short break.
I'm not sure it's very, I mean, let me ask and then we'll see whether it drifts. Yeah, so Ollie, I mean, the other two questions were actually, so you mentioned the loops. Mm-hmm. I mean, when you go from the spinice to this effective model, so do you think they're of any relevance or?
Well, yeah, this is something that we're kind of thinking about right now, actually.
Let me perhaps give a bit more background why I'm asking. So I mean, at least if you start with the, well, exactly on this slide, you have this tree-like structure, well, locally tree-like. Mm-hmm. So people have been looking at the Anderson model on such structures, and there was, I think for a decade, there was a discussion whether, unlike, say, 2D or 3D model, there might be an intermediate phase. So normally you would have localized, delocalized phase, but the claims were that on this tree-like structures, you might get an intermediate fractal phase, multifractal phase, or non-ergodic one. And basically people who opposed this view were claiming that precisely due to the loops that are present in these structures, but they're very, very long, this intermediate phase is washed away. So I'm basically wondering if, despite seemingly not to be important, whether the loops might actually be relevant in this.
Yeah, no, that's a very interesting point. So, I mean, when we say not relevant, what we're meaning is that this locally tree-like structure is able to sort of qualitatively describe quasi-particle motion on short time scales, which are sort of, I mean, at significantly larger timescales, you'll start to explore the loop structure of the lattice. But if you're actually sort of making some sort of semi-quantitative, but also sort of partially qualitative description of quasi-particle motion in spinice materials, it's less relevant. But from a purely sort of fundamental standpoint, I think it's something that we're investigating at the moment. I mean, we are personally interested in the addition of loops because like they do, and they have the potential to sort of very fundamentally change the localization properties, but only at longer time scales if you're thinking about quench dynamics. So from our perspective, like they will likely have sort of a very important effect on the properties, but those properties will only kind of manifest at longer time scales. And say in some case like this this mapping is already, sort of is already kind of semi-approximate in the sense that these spins are not precisely frozen in any case. So there's sort of a whole hierarchy of approximations anyway. But I agree, it would be very interesting to know what the what the effect of the loops is on the localization properties of the structure.
Yeah, and then if I may ask, so how do you take the loops into account?
As in, where do they come from physically, or how you would actually sort of pragmatically?
No, I mean, how do you take them into account? I mean, if you look, studying the localization properties, so say, how would you add a loop into the random com model?
Ah, okay. Yeah, well, I mean, so one way of doing that would be to sort of add random connections between offshoots.
So you simply randomly connect to a pair of offshoots, and then
so depending, so one direction that we're thinking about is kind of characterizing the properties of the structure, the tree-like structure, and looking at sort of the characteristic size of loop, frequency with which they occur, so on. And then you might be able to understand the properties by sort of adding in connections between the offshoots such that the typical size of the loops matches the characteristic sort of loop statistics in the original tree-like structure. But all of this, that's really sort of an effective model. And I think if you were interested in the study of loops, it's probably best to go back to the original exact formulation and then characterize it there rather than going via this sort of extra abstraction step. One potential direction is to think about sort of rather than going through this process of looking at a given spin configuration, identifying the possible microscopic tree, and then averaging over initial spin configurations according to the ice rules. Another option is to sort of do the abstraction in a slightly different way, and think about it as some sort of random regular graph, or even do it probabilistically instead. So deterministically remove a quarter and probabilistically remove 1/3 of the remaining bonds.
Mm-hmm.
And obviously it's then easier to generate the structures, and you'd be able to study the system slightly better. The nice thing about the random regular graph is that you kind of remove edge effects, unlike in this. So, but again, like the random regular graph is likely to be sort of a better approximant of the thermodynamic limits, in the sense that you're sort of minimizing the edge effects.
Right, but then I mean, then you will run into the problem that people had studying localization on a random regular graph, which is although I think by now it seemed to be settled to there being no intermediate phase.
But I think there are still some questions, right, about the exact location of the point, or that numerically I think it's still not 100% settled. There is still a little bit of controversy still, I think, about not having access to sufficiently large systems to completely
Well, maybe. Right, I think here I exhausted all of my questions. Thanks.
Thank you.
Okay, great. So seems like there are no further questions from the audience. So let us all thank our speaker once again. With this, I will officially close this PCS seminar. Again, Alexei, if there's a need for an extra discussion session, I'll keep the Zoom session open for you guys.
No, I think, I mean, I exhausted my questions. So I think if I have any further questions that come later, I'll just send an email.
Perfect, sounds good then. Great, so then I'll see you again next week, guys.
Thanks, Ollie.
Thank you all for joining in.
Yeah, thanks.
Ollie.